Start yet? Here we go. All right. So today we are looking at, and keep the noise down over there, you guys. The microphone's right here. Thank you. Slope functions. This is section 3.2. And so to illustrate slope functions, I put together this Desmos graph. So here I have a parabola, right? Nice U shape. And when x is -3 here, I get this point. It's not going to tell me what point it is, but it looks like it's the point -3, 2. I get a slope of -2. Does that look reasonable according to the tangent line?
Yeah.
Yeah. And if I move this point, is the slope going to change?
Yeah.
Okay. So if I move it over here to like -4-ish, I get a slope of -4. If I move it down to -2, I get a slope of 0, right? It goes horizontal there. So would you agree that the slope depends on which x value I pick? Yeah, so I got a function, right? You pick an x, out pops a number. In this case, it's the slope I'm interested in, not the y value of the curve. So I have a slope function. Okay. So let's write down some numbers. We're going to build a table and see what this looks like. So starting with x equals -4, the slope is -4. So x versus the slope of the tangents on parabola. So x is -4, slope is -4. At -3, the slope was, do you remember? But it was -2. At 0, the slope was, no, at -2, the slope was 0, backwards. When x was -2, the slope was 0. Let's look back at the graphical thing, double check. So if I drag that point over here to, where's 3? -3. Yeah, slope was -2. If I drag it down to x equals -2, slope is 0. If I drag over to x equals -1, I get a slope of +2. And if I go over to x equals 0, I get a slope of +4. So let's continue this. Let's see, -2, -1, slope was 2, and 0, slope was 4. If we were to plot these as points, x versus slope value, let's see, we went, oops, I need over here. That's -4, that's -2, that's -3, that's -1, 0, and then we have, oh man, I put my grid in the wrong spot. Select. Let's try again. I got some of it. There-ish, there-ish, and there. Let's do back up. Oh man, that's not going well. All right, that's a -4. Okay, so then what do we have to do? Slope down here, 2, 3, 4, -4, -2. So I get a point at -4, -4, right there, -3, -2. All right, there, -2, 0, right there, -1, 2. Right there, and then 0, 4. Right there. What do those points do? They line up. Yeah, they totally line up. Can anybody tell me the equation of that line?
2x.
Definitely the slope is 2, right? Because here we're going up by 2, up by 2. As y jumps up by 1 each time. Yeah, so the slope is 2/1, y-intercept is 4. So the equation of this red line is y equals 2x plus 4. And what we found here, this is a slope function for the parabola. Let's the other parabola I start out with. I believe it was y equals parentheses x plus 2 squared plus 1. Yeah, that's the one right there. So we found a slope function here, which is kind of neat. So now instead of having to use the definition of the derivative at a particular point and do the calculation, we can do it a slightly different way. So we're going to try this in 2 different ways. New page. Oops, button. So remember, slope at a point, x equals a is the point, y equals f of a is the limit as h goes to 0 of f of a plus h minus f of a all over h. And today we're generalizing that, and we're not going to pick a number for a. Instead, we're going to do slope function, which is very similar. Slope function is called f prime of x. It's also called the derivative function. And so it would be the limit, at least one version of it, as h goes to 0. And instead of picking a number for a, we're just going to leave it as x plus h. That's usually a tricky spot there. Minus f of x all over h.
This is like the number 9.
This was like number 9 in the homework, right? Except we didn't apply the limit. We just did a fraction. It's called the difference quotient. Yeah. So this whole thing here, whether we're talking about this one right here or this one right here, right? They're pretty darn similar. They look alike. One plugs in a number for x, the other one just sticks with x. That thing I circled is called the difference quotients. And when we find the derivative function here, what we're doing is we're taking the limits of this difference quotient. So just some language that you're going to see for the problems in the book. Difference quotient helps us find slope of a tangent, right? And with the limit turns it into a secant. So we're going to apply it to this particular function we were just working on. My function was f of x equals parentheses x plus 2 squared plus 1. This is called the vertex form of a parabola, and it's nice because it tells me what the vertex is. I can look at this and I can see the vertex is -2, 1. It's always the opposite of whatever's inside the square, and whatever number's outside is the y value. So I can say, oh yeah, vertex is -2, 1, so graphing is pretty straightforward. However, it's a little pain in the butt to work with the difference quotient, so I'm going to multiply this out and work with it. So I have to square x plus 2. So another version of x, f of x, is going to be x squared. I'm going to get a 2x plus a 2x, which is a 4x, and then a 2 times 2 is 4, plus 1 is 5. So that's another version of this same function. And we looked at a problem like this yesterday at the end of class. We're going to do it again today. I'm going to do the 4-step process for finding the derivative function. So again, what that means is to find the derivative function we call f prime, which is just a little apostrophe if you're typing something with this on a computer, is the limit as h goes to 0 of f of x plus h minus f of x over h. And I mentioned the other day that I consider this a 4-step process. The first is figuring out what the heck f of x plus h is. The second step is dealing with that subtraction right there. The third step is dealing with the division by h. And the fourth step is then finally trying to take the limit. So in order to do the first step, I need to remind myself that f of blank equals blank squared plus 4 blank plus 5. Right? So I highly recommend, if you want to get this part right, think of the function in that term, in those terms, and write it down like that too. What are we going to fill in the blank with? X plus h, right? So everywhere there's a blank here, I'm going to slap in an x plus h, an x plus h, and an x plus h. And so now I have to carefully simplify this expression. What does it mean to square something? Multiply it by itself, so I have to envision this guy right here as x plus h times x plus h. And most days I actually write it out instead of just trying to think it. So that's going to give me an x squared plus an xh and then another xh. So I'm going to get two xh's plus an h squared. And I move over to this there, I have to do my distribution. So that's going to be a plus 4x and a plus 4h and then a plus 5 at the end, just hanging out. And I think like last time, there are no like terms here. So I did this step, I expanded it. Most of the time we do need to do an expansion here. So if this was one of those problems that said, what is the answer to step 1? This red thing is what you would type into that box very carefully. I'm ready for step 2. And again, I get kind of lazy. I don't write a lot of stuff down. Sometimes it happens to you guys. Yeah, I bet. So, you know, I'm tempted to not write all of that out, but I'm going today, x squared plus 2xh plus h squared plus 4x plus 4h plus 5. And now I need to subtract parentheses, the original function. What's the original function?
2x plus
I'm going to use that version right there. Yeah, the x squared plus 4x plus 5. So minus parentheses, x squared plus 4x plus 5. And I put it in parentheses to emphasize the whole thing. Each piece is being subtracted here. But that's not too bad, is it? Anybody excited about subtracting x squared? I am, because we get to cancel stuff, right? So this x squared subtracts with that x squared. This 4x subtracts out with that 4x. And the 5 here subtracts with that 5 there, because I have to distribute that subtraction. So what's left? 2xh plus h squared plus 4h. So that's the simplified version for step 2. I have my numerator. What do we do next? Step 3. Divide by h. Okay, so I'm going to bring that to the screen. There we go. So step 3, I'm going to take my, what is it, 2xh?
2xh plus h squared plus 4h.
There we go. Thank you. Plus 4h. And none of those are like terms because they all have different versions of x and h in there. Divide that by h, which means each piece is being divided by h. Or you can factor out an h. There's 2 different ways to do it. Okay. I'm going to look at each piece being divided. So that gives me 2xh over h plus h squared over h plus 4h over h. And that gives me 2x plus h plus 4. If you chose the factor version of this up here, you would pull an h out, and then you'd have a 2x plus h plus 4 left in the parentheses. Right, and you can see the h's on the outside and the bottom cancel, leaving the same thing I have right now. Okay, so 2 different perspectives on the same algebra. So this is what I would enter for step 3 if this was one of those multi-step versions of the problem. So now I'm ready for step 4, which is to finally take the limits as h goes to 0. So step 4 of this thing, 2x plus h plus 4. And pretty straightforward, that h goes to 0, leaving just a 2x plus 4. Does that look familiar? That's what we found from when we looked at the set of points of a few different slopes based on the x value. So yeah, so we found it, which is kind of nice. Some of you may have noticed a pattern, or you may see a pattern when you're working on these. We started off with a quadratic function. Here, the slope function ended up being linear, which is kind of interesting. All right, so we'll test that to see if it works out all the time. Questions on this example? Okay. So let's take a look at some pretty pictures in the homework. And again, if anybody wants to respond to Peter, go for it. I see there's already a couple of responses. All right. Testing, exam, chapter 3, section 2, homework. All right. So here, which blue function is the graph of the slopes of the red function? Okay, so I have this red function here. What would you guess that slope is right there? 1. 1 is going, yeah, it could be 1, right? We don't have any scales, so it could be 2 or 3 or 1/2. But let's say it's 1. If that's 1, what's this one right here? Okay. And then there's some special x value that splits this in half, right? So the slope is 1 for a while, and then it switches to negative for 1 for a while. So now the blue graph is the graph showing the slopes. Which graph here could represent the slope being 1 for a little bit and then negative 1 for a little bit?
A.
Looks like A would be 1, B, and then down here would be negative 1. This one reverses it. That's maybe negative 1, then 1. Here, this might be something like 2 and then negative 1, right? So that doesn't quite work out. This graph is nice and symmetric. D doesn't work out. That would be something like maybe 1 and negative 3. Yeah, so I think A is the only reasonable option. Right. So we did find A. If this is the graph of the function, A is what the slope function would look like. It tells us the slope at any x value that we pick. All right. Next, we got a parabola type 1. The red is the original function. One of these lines is the slope function. Anybody have a guess as to which line represents the slope function? The green one? Yeah, and I heard somebody say something about the vertex there?
Yeah.
Yeah. Yeah, so green vertex. So if I think about it, if I look at this right here, I can see that at 1, there's a positive slope going on here, right? At 2, what does it look like the slope probably is? 0 is horizontal there because I go from positive slope to negative slope. If you go from positive to negative, what do you have to hit in between? 0, right? That's the intermediate value theorem. And on this side of 2, the slopes are negative. And green is the only function that is positive to the left of 2 and negative to the right. So it looks like green is the slope function, at least the best candidate to this red thing right here. Question?
What determines slope function?
To find the slope function at this point in time, we have to take the limit of the difference quotient like we did in that example we just pulled out. So we can do one like this in a minute. So let me see. I'm going to say it is green. And yeah, I get it right. Okay, so it's just a visual thing, trying to estimate what the slopes are of the red curve and say which of these other one is the best candidate for that. Ooh, this one's interesting. Okay, so the graph of the slopes of the red function has which color? So red is our original function. So let's see, the red has positive slopes for a while, right? In this region, picture the tangent line, positive, positive, positive. When does it look like the tangent line switches from positive slope to negative slope?
About 2.
Yeah, pretty close to 2, something like that, right? Pretty close to 2. And then, so it's going to go positive slope, and then after 2, it should have a negative slope.
Until about 5.
Until about 5, 4.5-ish, yeah, somewhere right there. Then it switches from negative slope to positive slope. Okay. So looks like, which one do you think does that of these other colors?
Blue.
Blue has negative values. So the blue, if the blue is the slope function, it would say before 2, your function should have a negative slope, right? Because blue has negative y values here. Okay, so it's not blue. Black before 2 has positive values. So it says if your function should have positive slopes before 2. And then between like 2 and 5-ish in here, your function should have negative slopes. And then after, let's see, which one am I on again? The black one? After 4.5-ish, your function should start having positive slopes again because it's giving me positive y values. Yeah, I'm pretty sure it's the black one. Yeah, pretty tricky. All right, let's try one like that. Got it. All right. So, new page. This is going to get interesting. I'm going to do a simpler version of that. That wiggly red graph was likely the graph of what kind of function? Do you remember way back when? Yeah, it's probably a cubic. So I'm gonna choose not a wiggly cubic, but a cubic that just goes up and down. So I'm going to take f of x equals x cubed. We have two choices for the derivative formula. I'm going to start off with the traditional one. So to find the derivative function f prime of x, I need to find the limit as x goes to 0 of f of x plus h.
Does h equal to 0?
Yes, h, thank you. X goes to 0. I'll miss these. Do you know there's a pressure point between the bottom of the middle of your nose and the top of your lip that will prevent you from sneezing?
Why don't you just think about bananas?
If you catch it in time.
Why don't you just sneeze? Or just think about
Well,
bananas?
in case I might have some viral particles in my nose, I don't want to disperse those into the room.
So wait,
live.
you just press like right on that weird like
You
dimple
just
thing?
press that little middle of that dimple area. Okay. Away from biology and back to math. So step one, I need to figure out what is f of x plus h. So I start off with f of blank equals blank cubed. And then into that, I plug in x plus h. X plus h. So we got a little work to do here, because this means to take x plus h times x plus h times x plus h. There is no shortcut for cubing something. Get busy. Time and patience, we can do this. I think that's what I get. Okay. So again, the way I approached it is we did the x plus h times x plus h before. I remember that one pretty well. And then I distributed the x to each of these and got the next three terms here. And then I distributed the h through and got the next three terms there. Notice there were some like terms, which is a little hard to pick out with all these x's and h's and squares and knots, but I'm pretty sure that's what it looks like. Something that makes me feel good about it, as I look at these terms, the x's go from x cubed to x squared to x to no x, and the h's reverse that. They go from no h to h squared to h cubed. There's a beautiful pattern flowing in each direction. There's a trick to these things you may have seen in a previous math class. So just side note, have you ever seen Pascal's triangle? Oh yeah, you got it. So Pascal's triangle looks like this. You start with a 1, and then you put 2 ones on each side underneath. Next row is 1, 2, 1. And the way you generate new rows is start with a 1, and then add the 2 numbers above. 1 plus 2 is 3, 2 plus 1 is 3, and then put a 1 at the end. So guess what the next row is going to be? 1, 4, 6, 4, 1. And you can just keep going on. Why is this important? Well, it turns out these are the coefficients of binomials to a power. So if you have something like a plus b and you raise it to the power n, then here n is 4 these would be the coefficients of raising a plus b to the fourth power. If you had a plus b to the third power, these would be the coefficients of that third power. The powers of a and b are kind of cool. As we can see in this example, they flow from whatever n is down to nothing, and then in the other direction too, from whatever n is down to nothing. So if you know Pascal's triangle and that pattern of powers, taking something to like the third, fourth, or fifth power actually isn't that bad. That make sense? Right. So based on that, if somebody told me instead of a plus b, if they said you have x plus h and you need to raise it to the fourth power, this and the declining and increasing powers will help you get there. So this means I would have 1x to the fourth plus 4, what's the next power of x? X to the third, and then the h's pop in, h to the first, plus 6, x squared, guess what h does? H squared, plus 4, what's the power of x?
X to the first.
Just x to the first, or x, what's the power of h? Third power. And then finally, I just have 1h to the fourth power. So that would be the expansion of x plus h to the fourth. In some algebra classes, pre-calc classes cover this, some don't. How many people have seen this in an algebra class before? About half the class. Oh, more than half the class. 3/4. Wow. Okay. Yeah. Kind of a cool trick. I'll point it out again next week. All right, so back to this right here. Can I do anything else? No, all the like terms. So what am I going to do next? Minus f of x. And I'm going to not recopy this whole thing. So step 2, I'm just going to make a note. I'm taking my f of x plus h, which is all of this stuff above, and I'm subtracting f of x. F of x is x cubed, right? So what's left is everything but the x cubed. 3x squared h plus 3xh squared plus h cubed is what's left behind. Step 3, divide by h. Okay, so we can get that right. Page, I have step 3, divide by h, which is going to give me 3x squared h plus 3xh squared plus h to the fourth all over h. And you can take 2 different approaches. You can divide each piece by h, or you can factor an h out.
H to the fourth.
Oh, it's h to the third, sorry. That was another problem, wasn't it? H to the third. Is that what you're going to point out, William?
It's say that you can factor
Back.
in each factor.
Yeah. Yeah, so if I factor the h out, I get 3x squared plus 3xh plus h squared. A number divided by itself is 1. 1 times something is itself, and the only thing left is in the parentheses, so I get 3x squared plus 3xh plus h squared, and I'm ready for step 4. Take the limit as h goes to 0 of that. What's left?
3x.
Just the 3x squared. So that is the slope function. So if y equals x cubed, then the slope function is 3x squared. So we're going to look at a graph, see if that works for us. If I had called this f of x, the slope function would be called f prime of x. Sometimes we just write a y instead, so I could say this is y prime. That's how I designate y as a slope function. All right, so I'm going to whip out a graphing thingy. Yes, it was telling me that I have another class in 30 minutes. Thank you. So let's see what I want. I want Desmos. And let's get a new Desmos tab. All right, so we have originally started with f of x equals x raised to the third. And the slope function, I think, is, I'll call it y equals, actually I'll call it g of x. G of x equals 3x squared. So does it seem reasonable? So let's see, if x were equal to 1, the slope, so the red is my original function, the slope there should be 3 according to the slope function. Does that seem reasonable? Well, we can check it. All right, so just see, g of 1 equals 3, the obvious there. So how do I find the slope of a tangent line? Sorry, not the slope of a tangent line, the equation of a tangent line. Y minus y1, yeah, so I got y minus, so again, when x is 1 here, y is 1, so I get y minus 1 equals the slope, what do I think the slope is? 3 times x minus the x value, x minus 1. And that looks pretty darn good. I'm going to turn off the slope function for a minute, turn off x equals 1, and just zoom in. That looks like a pretty tight fit there, doesn't it? Tangent line? Yeah, I think we did it. Yeah, and we could double check it by saying, all right, let's let g equal 2. And the slope should be 12. The point is going to be 2, what's 2 cubed? 8, so the point 2, 8 on the graph, so that's way up here. 2, 8 is right there. Does that black line look pretty tight to the red curve?
Yes.
Yeah, it looks pretty darn tight there. And I could zoom in x-wise by saying, let's see, what am I at? 2. I could go from, say, 1.5. Oh, oops, not negative 1.5. 1.5 over to 2.5. And yeah, that looks pretty nice. I have a nice fitting tangent line. So do we feel pretty confident we found the slope function? Yeah, we found it. Okay, cool. So calculating slope functions. I mentioned there's an alternate. Has anyone played with the alternate definition in their homework? One person?
I didn't
Okay.
understand.
Do you understand it? So I can do another example where I use the regular definition, or I could do an example with the alternative. Any suggestions?
Could you
Try the alternative? Yeah, I'm going to try it for this one, see how it looks different. And the only time you can't use the alternative are those problems that say, hey, go through those 4 steps, because that means use the traditional definition. And you never know which version is easier until you try something. So the alternate definition for a derivative function, I'm going to look at it this way. Derivative function, this is the alternate definition. It's, I would write it this way, take the limit as b approaches x of f of b minus f of x all over b minus x. I did it with a's and b's the other day. Here, I'm looking for a slope function, so I ultimately need x's to be everywhere. So this says b is going to morph into x. Now, if I cheat and just throw an x in there, I get 0 over 0. We're going to try it on the function f of x equals x cubed, the one we just did. See if it's any easier. So for my limit definition, f prime of x is going to be the limit as b approaches x. F of b is just b cubed. F of x is just x cubed, all over b minus x. Yeah, doesn't look too bad. If I try to cheat and plug in x for b, what happens again? I get 0 over 0, which is a problem. So either I have to be able to carry out this division and hope it simplifies and that denominator goes away, or I can hope the numerator factors. And this denominator happens to be one of those factors. I'm going to go for factoring. Anybody remember the formula for the difference of 2 cubes? So this is a formula you learned in algebra class. You were probably told to memorize it for a week and then you forgot about it. So usually it's stated with capital A's and capital B's. So a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. That's a b, that's a square. And we will by b. That's the difference of two cubes. So for us, I have a little b there, and I have a small x here. So for me, the factors would be b minus x times b squared plus bx plus x squared. So I got one of the factors I was hoping for, which is kind of cool. Give me a minute to take that in. Otherwise, we could have tried long division on this or synthetic division with b's. So back here, I now have the limit as b goes to x of b minus x times b squared plus bx plus x squared all over b minus x, which is a beautiful thing because those guys divide out, and if I let b go to x, then I get x squared plus x squared plus another x squared, which altogether gives me
3x squared.
Gives me 3x squared, which we discovered the other way. So instead of 3 pages of algebra with the other formula, this one took 2 pages of algebra. Because I really did have to use that. Remember, I used that second page here to figure out what the heck that numerator was. And I had to know that formula. If you didn't know that formula, what would you do? Long division with x's and b's is a little bit of a nasty sucker. Yeah, I'm not going to do that. If you want to see that, visit me after class. I'll buy you coffee. All right, so I got the same function. So again, it's kind of a matter of style in some way. You could choose either definition, unless I specifically say use the traditional definition, like use that 4-step process.
You'll never say use the alternative.
On a test, I will usually not say which version to use. I will just say use a definition for the derivative to find me a derivative function with a slope at a point. And you can
Good,
pick.
I'm only learning one.
You pick whichever one you like.
I'm
Okay.
only learning the first one.
Yeah, that's cool. You guys have a choice now. Choice is one of the most wonderful things about life and one of the most dangerous things. All right, let's take a look at a homework question. We get about, what, 10 minutes, 11 minutes? Usually the ones near the end are more exciting. Second derivative, okay, yep, that's exciting. Ooh, differentiable, yeah. First derivative. Yeah, we can do a couple. So I'm going to talk about differentiability.
No.
What does it mean by first and second derivative?
Yeah, we'll take a look at that one next because Peter Parker asked a question like that from the take-home exam.
I don't know why you still refuse to say it's you.
Oh, that Spider-Man is a part of our calculus class.
Your last name was Parker. Why would you name your kid Peter?
Like, because
You could be a Spider-Man fan, or you've
asking
never
for
heard of
kid.
Spider-Man and you just
Yeah.
think Peter's a great name.
One day you're registering your kid for school and the
I have a-
attendance.
I have a dear friend named Peter. Okay, so let's take a look at it. So we looked at the idea of continuous in the last chapter. So a little review of that. Continuous. Continuous is a 3-step process, right? The steps are 1, does f of a exist? We hope it does. 2, does the limit as x goes to a of f of a exist? We hope that it does. And the third condition is that the limit as x goes to a, oops, that's supposed to be an x there. Didn't get to a yet. There we go. And of f of x, that actually matches the function value. Okay. So if you have those three conditions, that means you're continuous. So points I'm concerned about, at the point -1, 2, it looks like I have, is this function continuous?
Yeah.
Yeah, it looks like it goes up and then down, a little pointy, but yeah, it looks like it's okay. How about at 1?
No.
No. So which rule did I violate for continuity for at x equals 1?
Limit f of x as x goes to 8 does not
The limit does not exist. Yeah, since 2 is out, that means 3 is out automatically, so it's not continuous at x equals 1. But it does look like it's continuous everywhere else. You know, let's assume, at least in the domain that I can see, from -5 to 5. And maybe it continues like that, and it continues like a parabola there. So this function would be continuous everywhere except x equals 1. That's continuity. Differentiability is kind of similar. So differentiability. One way to think about differentiability is the derivative function is continuous. So what does the derivative function tell us, right? Derivative function is a slope function, right? So as long as the slopes form a continuous function when I graph them, then I'm okay. Now, if we have a break in the function, then the derivative function is going to have a problem. So if you have a point where it's not continuous, the derivative is going to be messed up in some way. Okay. So for sure, this particular function is not differentiable at x equals 1. The question is, are there any other points of concern here that it could be not differentiable at? What's that? At -1, we have that pointy thing. Yeah, let's look at that. What does the slope appear to be over here on this side? Looks like it's about 1, yeah, according to this. So it looks like I have a slope of 1 going up to the point where x equals -1. But what does the slope look like on the other side? It's not 1. So those slope functions match up there? No, they're broken. They're broken there. Okay, so that point's going to screw things up. So at x equals -1, we're also not differentiable because the slopes will not match there. It turns out pointy functions end up being a problem for slopes. Slopes break on pointy functions. Over here, I have a peak. Do I have a problem at the peak? Yeah, the slope is positive on this side. It smoothly goes to a negative slope on that side, and it looks like it's probably going to have a slope of what right in the middle?
0.
Slope of 0 in the middle. And we saw that in another parabola. That's going to be okay. Pointy stuff's a problem. So coming back to the problem, it says, it gave me some choices for troublesome x values. My troublesome x values are -1 and 1. Otherwise, I think it's okay. Wee-hoo. Got it. All right. 13, second derivative. Ooh, yeah. Okay, let's do it. Screenshot this sucker. Hopefully I can finish it in 6 minutes. Screen. All right, so we need to do two things here. We need to find the first derivative, and then we need to find the second derivative. So just note, first derivative means apply some derivative definition. Take your pick. I'm going to use the traditional one. F of x plus h minus f of x over h. Take the limits. H goes to 0. Second derivative just means take the derivative of your slope function. So then we'll find f double prime. That's going to be the limit as h goes to 0. But instead of f, I just throw whatever I found f prime to be. So I just repeat this process for whatever function the first one gives me.
So why do we need the second derivative?
Good question. So suppose this thing talked about the position of an object over time. The slope is the speed of the object. If we take the change in slope, any idea what that gives us? Change in speed?
Velocity.
No, speed is velocity. It's acceleration. Yeah, if you speed up, you accelerate. If you slow down, you decelerate. So the second derivative in terms of like position type stuff talks about acceleration. Other places it talks about that's important. Consider, suppose this is a population increasing over time. Populations can't increase forever. Eventually they start to slow down and reach some capacity. So over in this region over here, my slopes are positive and they're getting steeper, right? But then all of a sudden I reach some magic point in the middle where the slopes start to decrease again. So I have a change in the speed that the population was changing, right? And so it turns out it's important in just about anything you can track. You can not only look at the rate at which it's changing, but you could see if it's increasing at an increasing rate over here. But then on the other side of that magic point over here, the function is still increasing, right? It's still going up, but the rate at which it's going up is dropping. So this is now increasing at a decreasing rate.
And so then that would be at double prime?
That would be, yeah, to talk about the change changing, that would be the second derivative. Increasing at a decreasing rate. Decrease. Yeah, and that comes up in mathematics and finance, biology, medicine, you name it, it comes up. So the hardest part here is going to be finding the first derivative because we have a cubic to deal with, and then otherwise the second derivative is not going to be too bad. So we have time to do the first derivative right now. So back to doing this one, I need to find, step one, f of parentheses. So that means rewrite the function with parentheses, -2 parentheses cubed.
Squared, not cubed.
Did you get to that pressure point in time?
Squared. It's squared, not cubed here.
That's a cube right there.
Are you sure?
I'm sure, yeah. Let me blow it up for you.
Okay.
It is a cube.
Okay.
Okay, stick that down here for now. All right, so then we've got what? Plus 6 parentheses, plus 50. And then into that, we're going to drop our x plus h, our x plus h. And then we just have to be really careful. Now we saw the pattern for the cubic. Okay, so you can look back at your notes for it. So that's going to be -2 times x cubed plus 3x squared h plus 3x h squared plus h cubed. Plus 6x plus 6h plus 2. And then I get to distribute the -2. Minus 6 x squared h minus 6 x h squared minus 6h cubed, and then plus that other stuff. So your homework's just going to involve very careful algebra. Any like terms? Nope. So then I get to subtract the original function, right?
Yeah.
Right. So when you subtract, you add the opposite. So that means adding the opposite is going to give me that. -2x cubed plus 2x cubed goes away.
6x here.
6x minus 6x goes away.
And the 2 goes
2 minus 2 goes away. We're out of time for fun with math. Think you guys can finish this? We'll do some more of these tomorrow, review for the test. If you haven't already, look at the practice problems online, look at that sample test. If you have questions on it, post them to the forum like Peter did.
Double prime, I put f from x plus 8 and that one. Subtracted by this f of x and then roll it again.
Yeah, so when I finish this up, right, I'm gonna get, where's my magic pen?
Whatever it is, and then you just put the entire process in here.
F prime of x here is going to be -6 x squared plus 6. And we clean that up. So now I apply to that
Okay.
the limit definition. It would be the limits as h approaches 0, and this is your new function that you're going to plug in.
Could you just keep taking the derivative of that function until you got a number? So like you got
Yeah,
next to this.
eventually, yeah. So if you take the derivative of a cubic, you get a quadratic. Take the derivative of a quadratic, you get a linear function.
Like
Take the
linear,
derivative of a linear function, you get a constant. You take the derivative of a constant,
you can't.
you can, yeah. Constant's a flat line, so it's always 0.
Oh.
Yeah, eventually it gets
So we're gonna get
zero.
it linear after that.
Yeah, the derivative of this will be a linear function, correct?
I had heard.
So are you taking?
Exciting.
No, the test is Friday. Tomorrow is review.
I don't think I'll-
Okay. Yeah, so I'll be recording the review.
I got a problem for the.
Hang on, let me
Oh,
pause.
yeah, I got that one there.